All right, thanks very much. So my name's Greg, and I wear a couple of different hats. I'm a research director for Borealis AI's Vancouver office, and that's sort of my full-time job, but I'm also, I guess I'd call a recreational professor. I've been a professor at SFU for 15 years as well, and I still do teach there and have PhD students at SFU as well. So I'm going to talk to you today about activity recognition and video analysis. So that's been one of the main things that I've worked on as an academic for the past 15 years. And it also underpins a lot of the work that we do at Borealis AI. So at Borealis AI, we're a bank, we're part of RBC. We don't have a lot of pixels, is kind of my line, but we have a lot of temporal data streams. So credit card transactions, financial data, and so a lot of the models that we develop in video analysis are also very much the type that we use in Borealis AI. But for this talk, my goal is to really talk with you about what has happened in the field of human activity recognition over the years, so give a little bit of a history of what type of work people have done, a lay of the land of what types of problems that people work on, as well as hint at some sort of future directions. I think many people in here are either master's or junior PhD students, might want to be thinking about like what types of topics you're interested in studying. I'll give a bit of sort of directions that I think are important emerging ones that are going on in this field. Okay, so to sort of set the stage, what do we mean when we say we want to do activity recognition? What we want to do is take in a video, such as a frame here that's shown from one, and we want to kind of understand what's going on there. So what subproblems does that involve? The first one you might think of is detecting people. Where are the people in this scene? The state of the art these days is that these types of problems are almost solved problems. I mean, to the degree that you can kind of reliably detect every single person in the scene, we have algorithms that are capable of doing that. But beyond that, what we like to be able to do is understand what's happening. And to understand what's happening, we need to do a number of different things. Some of these problems are things that Angel probably talked about in the morning session about images, understanding objects and scenes. So to understand what's happening here, we'd like to know that these are people who are in a long-term care facility, there's a chair, there's a walker, there are various objects that are present in this scene as well. We'd also like to understand actions of humans. So what are these people doing? This person's standing, this person's running, this person has fallen down. That's another what we call sort of action recognition, which would be put these tags or labels on each of the individual people in this scene. But again, it's not necessarily enough just to know that that person is running. You might want to know why that person is doing this. So for example, that person is running, but she's running to try to get help. That person is squatting, and she's squatting to comfort the fallen person. So there are many different levels at which you can label this person, and also label what's happening in this scene. So we could also characterize the entire group of people. What are they doing? This group of people is trying to help a fallen person. We could do that either in sort of a label or tagging sort of version, or we could imagine trying to caption this entire scene with a set of sentences such as the ones shown up there. So all of these problems together, this is what we mean by sort of activity recognition. It's not just this level of labeling this person running. That's really not enough to understand what's happening in a complex scene such as this one. We really want to try to address all of these things. And all of these things are interrelated. And essentially, we're trying to solve kind of entire AI problems around fully understanding what's happening in a scene, being able to describe it, answer questions, and characterize it at multiple levels of detail. So this is an important problem. There are many different sort of verticals or application domains in which you encounter the problem of taking an image or video and try to understand the actions. So we have sort of the canonical kind of user video sort of situation where there are hundreds of hours of video that are uploaded to the internet. You want to do kind of indexing and retrieval type tasks to figure out what's happening there. There are sort of streaming videos that occur 24/7, often in a surveillance context. Either that's for security or that's for monitoring or assisted living types of applications, where we want to develop algorithms that can automatically process those videos and figure out what's happening for those people in a scene. There are also lots of applications in media, so in tasks such as sports analytics, either trying to understand what players are doing in a scene, do that for the purposes of media or content analysis or recommendations of different players and strategies to employ in sports. And finally, there's sort of a lot of effort in wearables and robotics, where you're basically trying to deal with either person-mounted cameras or cameras mounted on mobile robots, trying to let those agents interact with people in the environment. So you want to be able to characterize what are people in a scene doing so that you can behave naturally in a scene if you're developing a mobile robot application. Okay, so the challenges that we face are in common with many visual recognition problems, but they also do have some things that are peculiar and particular to video. So the first of these is sort of that there are large variations in appearance. So this is true of many objects, but if you think about something like action recognition, these two examples are both from a data set, the action hugging. This sort of the background scenery, the pose of people, the clothes they're wearing, all sorts of things can vary quite dramatically. The thing that's, I think, particular to video and particular to action recognition is the challenge of collecting a lot of labeled training data is very difficult when it comes to video. It's harder to get the diversity in scenes that you would like to have. It's harder to label things when they're spatial and temporal. You don't have access to the quantity of labeled data that you have for image type recognition tasks that require sort of large amounts of data to be successful. And then the final thing, and again, this is in common with many things in visual recognition, but the vocabulary is not well defined. All three of the examples at the bottom are from a category that's known as open in a data set. So you can open an umbrella, you can open a door, you can open or turn on a tap. Each of those is very, very different in terms of what it looks like visually, and yet they still will have a kind of the same vocabulary tag for many of the data sets or many of the ways that we have for acquiring labels. So these are challenges that sort of make video particularly difficult to deal with, especially this kind of labeling lots of data and understanding the right vocabulary to use. You can also characterize the type of problems that we work on in terms of the level of detail at which we're trying to understand human activities. On sort of one end of this axis, we have relatively simple gestures. So these would be things like standing or pointing, where it's typically a single person who's performing some sort of atomic action with a very short time span. At a longer level of detail, we might have something that's just not sort of episodic, but something like waving your arms. That might be an action that persists over a slightly longer time duration. We also care a lot about human-object interactions, so it matters where am I doing something rather than just what sort of things are in the scene. One of my favorite examples of this type of thing about how interactions with objects and scenes and what you're doing is very important for understanding actions is the following. So how would you describe what I'm doing right now? Like what vocabulary would you use to say what am I doing? If you were looking at the level of kind of gestures or actions, what types of words would you use to describe me? Standing, talking? Okay, so giving a lecture is good. So standing, talking, moving my hands. Okay, if you take me and you say I'm giving a lecture, okay, this is good. You think I'm giving a lecture, I hope you're paying attention to me. This is good. Okay, so if you took me and put me outside on the street by myself, and I was doing exactly the same thing, what would you say I would be doing? I hope you'd be concerned for my well-being. I hope you'd be like, wondering about what he's doing. You probably wouldn't sit here for 75 minutes and pay attention to me and say, okay, I'm going to use that in my PhD work. Okay, so this kind of the context and the interaction with objects and what's going on around you is very important when it comes to understanding actions. Right? So it matters, these human-object interactions, detecting the objects in the scene, detecting what's going on. It's more than just the body pose and what the person's doing. Okay. And so there also are some situations where you're interacting with multiple people. So it's not just understanding actions of an individual, but it could be interactions between a pair of people. Like, are these two people going to have a conversation? Are they going to shake hands? What's the likely thing that's happening in this type of scene? And then we kind of a little bit further along, we go to what we call group activities, where it's not just a pair of people interacting, but maybe it's a big crowd, maybe it's a team sports type of event, maybe there are things that are happening at the scale of multiple people. Okay. So, as you are well aware, the standard way in which we solve this problem is we use, machine learning techniques to get sort of labeled data, typically supervised learning, get a bunch of labeled data, represent those in some way, build a classifier so that when we're presented with a new video, we'd like to kind of say, where does this likely lie, and say, okay, this too is an example of a punching video. The important thing to note about the videos that I've shown here is that they're all sort of segmented. Okay, they're all sort of cropped in time to a relatively short instance where we know that something is happening. So this version of the problem, we usually refer to it as activity classification. The idea is that the input is this cropped in time chunk of video, relatively short, and the question we're asking is, what is this? And again, as you may understand, this is a very small kind of part of the problem of activity recognition. Much of the world is not presented to you in this sort of format, but this is what a lot of the effort that you have in the research community is about, is how do you classify a video into what's happening? So we usually refer to this as classification. And there are a number of data sets that, oops, sorry, pushing the wrong button. There are a number of data sets that are out there in the literature that are used for measuring kind of the performance of classification data sets. Here are some examples there. Many of them are derived from feature movies, so kind of 2-hour-long videos for which people have gone through and manually marked out, here is an instance where somebody was drinking from a cup. Okay, they've gone through that long video and cropped out this little chunk of video. Your job is to recognize that that was drinking from a cup and not, flying off the walls or some other thing that's happening in that other clip of video there. Another thing is that people often download these videos from YouTube or other sources on the internet. So again, short video clip, what's happening here? Someone's spinning a pizza. Other one, short video clip, someone's taking a basketball shot. And again, I think you appreciate how this is a smaller version of the problem. The bottom right-hand video, this is someone just taking a basketball shot. Likely, you could have an hour-long video in which that snippet of action, you need to go and find that in a long chunk of video. So we refer to that problem, the one where we're actually posed with a longer video and we need to find where the actions are in time, as activity detection. And activity detection can refer to both sort of finding in time as well as finding in space. We also sometimes refer to as activity localization. So the goal there is to go through a long video, maybe a feature-length film, and say, here is where there was an instance of the action hugging. There are different ways in which you can represent this. One way is to say that there will be a duration of sort of this point when time was hugging. Another way in which people do this is on every frame they put a label, right? So this frame had standing, this frame had hugging, this frame had hugging, this frame had hugging, this frame had hugging. A question, like, do you have any sense of are these two things equivalent? This versus that? Like, are these the same thing? Is there anything different about these two output representations?
I think the segment is harder because if you want to predict the segment, then you don't have this on and off, so you have to smooth these small predictions.
This is a good point. Yeah, it's a really good point. So you're saying like, it's different, like this is a harder thing. You have to sort of smooth things and know that there's this. Does this, if you had this output perfect, would it be enough to do that? If you have this perfect, is enough to do that? The order? I think so. Like this, same, different? Yeah? Yeah, okay, so there's multi-label. There's the other thing that wasn't shown here, but a frame can have multiple labels. Okay, so here's one important thing. How many times did the action hugging occur in the video? This answer represents that answer. This doesn't. This could have been, how many steps did you take? Were there, 5 people who were, doing different sort of things? Were there multiple things happening at the same time? This type of representation is often better, right? So this sort of thing where you actually annotate temporal durations and say multiple possible such things is often a better type of representation. Okay, so how do we do that? Again, there are data sets that exist in the literature. Again, if you're interested in this field, there are things like charades or multi-thumos. Multi comes from the fact that it's multi-label. So there are snippets of action that are represented via multiple labels in time. So the standard kind of way to approach this problem, if you're looking at sort of activity detection, is to take those binary classifiers that we have for classifying a whole video. So for example, if we had a classifier that could take in a video and say, was that a push, yes or no? Taking this one and say, yeah, that's a push. And that binary classifier can also take in a short snippet of video and say, that video, no, not a push. If I have access to something like this and I wish to do temporal detection, a very naive way of approaching things is just to take my long video and then run that classifier over all possible temporal segments at many different temporal resolutions, so sort of, small scale, medium scale, larger scale, and see where that thing fires and say, okay, that's a pushing action right there. Okay, so that's sort of a way in which people can take a push, non-push, simple clipped video classifier, then extend it to doing detection in time. Further beyond that, people often want to do actual spatiotemporal detection. And again, this can help answer the question not just, is there running in this scene, but how many people were running, where were they next to each other, for how long did they run, et cetera. So that type of problem we refer to as sort of spatiotemporal activity detection, and our goal is to put bounding boxes often around the people that are present as seen, again, annotated in space and time about whether they're performing a particular action of interest. I'm going to dive into a bit more detail on activity prediction and these methods later on in this segment. Okay, so the other type of problem that people often work on is trying to predict what's going to happen in the future. And here are two canonical examples of ways in which people formulate that problem. One of them is what's known as early recognition. So the early recognition problem is I want to be able to understand that something's going to happen as soon as possible. Right? So for example, if I'm trying to detect a throwing action, I'd like to do that not post hoc, not after I've seen the whole video, but I'd like to do it in real time as soon as possible, so along the way to the person actually performing throwing. So I've got some sort of binary classifier that I'm running in time, and I want to predict throwing as soon as I can based on that. The other type of prediction that people often want to accomplish is to be able to infer future activities or locations based on the current information. So if I see this right now, what's likely to be the action that follows? Right? So for example, if I see that frame, maybe a throwing type of frame is likely to result next. So these kind of activity prediction or forecast is another task that people work on. Okay, so that was kind of like sort of fast sort of intro to here are the types of problems that people work on in activity recognition. And again, this field's been around for quite a long time. Some of the early work that existed was sort of in human vision and psychophysical sort of experiments about trying to understand how and whether people can recognize different actions. Some of the seminal work in this was done by Johansson in 1973. There were these really beautiful experiments on showing people moving light displays where they had kind of lights that were attached to body joints, and basically seeing if that's enough information for people to recognize the activities that are present. So I don't know if you sort of see these sort of moving light displays. Just from the positions of the body joints, it seems like you can recognize what actions are taking place. Right? There's someone climbing over something, someone walking, someone throwing, et cetera. The studies are actually really beautiful. He also did work on kind of from unusual angles. So if you take that same sort of throwing motion that we're viewing from this sort of frontal direction, instead if you imaged it from up above, people have almost no idea what's going on. It's very hard to interpret these stimuli if they're viewed from an angle in which you're unfamiliar with. There's similar types of experiments on gait recognition, so being able to recognize your friends or recognize people you know based on similar types of stimuli, again, from varying distances. So this type of sort of psychophysical work spawned a lot of work in the computer vision community. People worked on trying to automatically classify actions based upon pose estimates. So if I know where the ankle, wrist, elbow, shoulder are, can I use that as a means to recognize action? Another seminal piece of work was in the early 1990s. So I don't know if you can imagine what it was like in the 1990s doing computer vision. The techniques you had at your disposal were things like hidden Markov models and background subtraction. But there's a really beautiful paper in the 1990s on how do you use those techniques to build systems that can recognize actions. And it's funny, like if you take that paper and you replace background subtraction with ResNet 152, and you replace hidden Markov models by LSTMs, that's kind of a paper from 2015. So that's good, but almost everything that goes into it is the sort of ideas that we had in those days as well. And there's similar things along the way where people did these sort of 3D body posture-based recognition, again, motivated by Johansson's stimuli. People did work on human-human interactions, again, using variants of hidden Markov models and structures that are used for that. So the moral of this story is basically there are a lot of really great ideas about these problems and building structures, but the techniques that people use these days are sort of improved upon in order to do a better job at recognizing things. Okay, so we fast forward past a lot of this work to kind of the current day. This is how sort of like your basic traditional video analysis pipeline would work, right? So if you're building one in 2019, generally what you're going to do is the following. You're going to have some video data as input. You're going to run something that's going to process that, which is going to be some form of convolutional neural network, and I'll show you some examples in a few slides. And then we'll put those through some sort of classifier that's probably built into that, and then get an output which says, how likely do I think these various labels are likely to be taking place at some point in time, all right? And so as I mentioned, these days we're doing CNN type architectures that do that with lots of parameters that are sort of optimized for representing the data that we have access to. Right, so some examples of what this looks like. So video classification with CNNs is slightly different from the things we do in images, but borrows heavily from there. So typically what we have is we have architectures that will take in two different sources of information. One of those is about sort of an individual frame, so the appearance of what's happening in one frame. The other side of which is taking into account what's called optical flow or motion information. And that motion information is computed via representations that span time. Right, so those two representations are each developed often with their own convolutional neural networks and then are fused in some way, this plus symbol used to denote some sort of fusion operator such as concatenation, which will take these streams from images and streams from optical flow, fuse those together in order to figure out what's happening in a video sequence. And there are lots of varying architectures that are built that are either processing frames individually or taking blocks of K frames and analyzing those collectively as a whole. So as example, here's some architectures from Andrew Zisserman's group on kind of analyzing series of frames, standard sort of things around conv operators, pooling operators, and people examine where and when to do fusion between these different streams. So one can either kind of look at the optical flow stream in isolation, look at the image stream in isolation, fuse those, or do sort of various combinations of early and late fusion to examine things. The other class of methods is typically to more directly work on a 3D volume representation of a video rather than computing an optical flow signal separately from an image sort of analysis routine. In those circumstances, what you have is you have this volume, which is sort of an H by W by L kind of time volume, and you build 3D convolutional filters that operate directly upon that. So in this case, rather than having kind of a spatial con filter that you would have for a normal sort of image type processing thing, you'd have a volume that you're convolving spatially and temporally over top of a video, right? And so similar sorts of things that you would do in time, you do those things that you would do in space. Okay, and finally, we just had a great lecture on RNNs. There's a whole bunch of work that uses recurrent neural network type architectures, either LSTMs, GRUs, or other variants of those to try to process what's happening. Okay, so that's sort of the very quick introduction to video processing and what happens in kind of modern video analysis techniques. So the rest of this talk I want to dive into three different problems in detail. So I'm going to talk a bit more about action localization. I'm going to talk about group activity recognition, and then I'll talk about generative models and finally conclude with some future directions. Okay, so action localization. When my friends ask me what do I do, many times they, we do stuff on YouTube video analysis. And they're like, no, like what does that mean, YouTube video analysis? And I say, well, finding cat videos, right? Like that's it. People want to find cat videos on the internet. We build algorithms that can help you find cat videos. Okay, so I promise I'll show you some cat videos in this talk. Here's my cat video. Okay, so this is sort of action classification, okay? Here's a video, cat. That's the sort of label we want to put on that. Action localization wants to do much more than that. We'd like to know that this is a jumping cat, and beyond that, we'd like to know, is it this type of jumping cat? Is it this type of jumping cat? Is it this type of jumping cat? Those are all sort of different things. And again, the reason that I would care about that is that in most applications, it's much more important to say more than just walking person. Okay, so if this video was put in and all you could say is walking, I don't think it would be very useful, right? We actually really want to know where and when these people are walking. And this particular thing, we can see there's a standing person there, there are these people who are walking, there are these interactions with vehicles and other people. We want to be able to understand this sort of level of detail of what's happening. Okay, so how do we do this? I was mentioning before that a very common representation for action localization is a bounding box. So we're going to represent each person with a rectangle in every frame. And we can generalize that to time by doing that in every single frame and having this type of cuboid type representation. And what we want to do is build algorithms that can have a very high intersection over union, it's called, basically produce an output that overlaps heavily with the ground truth labeling, and we measure that over every single frame. Okay, so if you remember what happened this morning in Angel's lectures, I think she probably talked about mask RCNN, faster RCNN, all these sorts of things. Okay, so there's a lot of commonality between action localization, video analysis, and object recognition. In fact, I have an algorithm that if you want to work in activity recognition, here's how you produce a CVPR paper, okay? Here's my algorithm. I don't know if you get my joke or not. Okay, so how do you produce a paper in activity recognition is you read a paper from last year on object detection, and then you say, oh, that's a really good idea. I'm going to do that for action detection. I'm just going to replace all this stuff and run some TensorFlow concat operators to throw in things that are different. Okay, so there is a lot of this that for better or worse, goes on in the community. But there are some challenges I think that are important in particular that I think are actually interesting about studying action localization compared to doing object detection. So one of these things is that kind of the simultaneous actions, and particular simultaneous actions with non-overlapping temporal extents. This is something that I feel is particular to action localization, which is that you can do more than one thing at the same time. Right? Like I can be giving a lecture, I can be pointing, I can be talking, I can be doing these things, and the time spans for those will vary. The other thing that's hard is that the start and end points for many actions is very unclear. Right? So it's quite difficult to label when does a basketball shot, when does that start and when does that end. Right? There are a lot of things that happen before and after that are difficult to label and annotate. The other thing that's particular in action localization is that the search space is much larger. So if you think about trying to do object detection in an image, your problem is to search over possible spatial locations and scales for where that action or object is taking place in one frame. If I have to do that in time, I've got this challenge of doing exactly the same thing to the power of number of frames for which that action is going to exist. So building algorithms that can actually scale in that way is very, very difficult. And the kind of analogies between actions and objects kind of break down for many of these things. It seems very difficult to build algorithms that would do things like what mask RCNN or YOLO would do, where you propose anchor boxes and propose possible locations for actions. It doesn't seem easy to do that. So a lot of the work that's out there is about trying to see how you can build more intelligent ways of doing that. But an example of how to, like an older architecture for how you would do action detection in videos based on kind of mask RCNN or RCNN type architectures is the following work by Georgia and Jitendra. Basically what you would do is in every frame of a video, you would treat it just as a separate frame for an object detection system, detect all of the possible people in this scene, analyze each of those, get sort of CNN-based feature representations out of there, concatenate them together, and classify them as a whole. Subsequent work kind of looked at trying to build more directly, combining the idea of anchor box regression of where the spatial extents of things are, combining that with classification of what that action is. So trying to build methods that would actually say, this person in this scene is likely to be a frame of a person who's doing a golf swing. This frame in one scene is likely to be a person who's doing standing action. Building those in at the same time while you're doing your proposal systems. Other approaches basically try to alleviate that temporal issue by building what are called microtubes in time. So rather than having the representation being just a single frame and a rectangular box there, you would try to build a small tube which is likely to contain a single action only. So a little track of a person with a rectangular shape around it where I'm pretty confident that there's only one action taking place there. Those would then often be combined with a final kind of linking stage where you'd have to kind of combine those short tubelets to form an entire action. Similar work in this vein, some work from Jiawei, one of my students, was on kind of how do you build those, but do it in a class agnostic fashion. So rather than doing detection of tubelets that are specific to a particular action, doing that in a general sense, the reason being that it's quite difficult to detect, build a classifier that can tell the difference between a walking person and a standing person, where one is a positive example for one category and a negative for the other. Finally, I'd highlight that there's creative work going on as well in kind of what type of supervision one should use for training these methods. All the work that I mentioned up to now would require fully annotated, labeled bounding boxes around all of the people in every single frame. That's quite arduous to obtain in many domains. So people worked on what's called pointly supervised learning, where rather than having to annotate bounding boxes directly, you can just annotate with a few points. Where is the person performing an action throughout a video, and then have techniques that can kind of clean up that type of representation over time. And again, if you're interested in this kind of line of work, there are data sets here. What I'd point to is that the scale of these is far, far smaller than everything that exists for image classification. Like the image net of this type of work is far, far from what you would need to train things well. There are data sets like ActivityNet. One of the bigger ones that we have is AVA, Atomic Visual Actions. It only contains about 80 actions and has 430 video clips that are densely annotated with lots of information about where and when the actions are taking place. And so I think this is what's sort of exciting about trying to work in this field is you're trying to work in a way that you do not have access to the quantities of labeled data, trying to build techniques that can still scale in spite of that. All right, so the short thing is this was a brief highlight into kind of action localization. State-of-the-art systems are generally derived from state-of-the-art in object detection, but there are important modifications you need to make to handle the large scale space, multiple actions, temporal extent, actually being able to do end-to-end training with these models. And I think that there are, again, a lot of exciting open issues that exist here around defining good label spaces, what to recognize, how to localize complex actions. So if you have a very, something that's a complex thing like giving a lecture, how would you actually define a localization for that type of thing? How do you do kind of tubelets, or what's the right output representation? So maybe we'll just sort of pause for a second just to check if there are any questions or anything people want to check with. Otherwise, I'll push on to group activity recognition. Any questions at this point? Very good. Okay. All right. Oh, sorry. Yeah. So a good question, like, is it more important to be kind of precise or do things in real time? So I would say that the definition of the problem is important. I alluded to this problem of batch offline processing where you say, this video contained 5 people who were running and they ran at these points in time. That's one version of the problem. The real-time or online detection is another one that's very important. So there's a lot of interesting work in how do you do recognition as soon as possible. So it's a nice version of the problem where you're trying to optimize not just classification accuracy, but the time delay with which you can make that classification. So both of those problems are interesting depending on the application, but that time lag based one is useful for real-time applications. Okay. Yeah. Yeah, often these microchips are often combining object detection with tracking algorithms. So you imagine that you have this problem like trying to track a person over time. You basically want to say, is this a person? And is it the same person? And is that person performing the same action? That's the idea behind these microtubes, is that rather than just having a single frame, you'd like to build a small tube. The rationale for this is that it's often easier to make a classification decision. Like say, is this a walking person? If I have 12 frames where I'm sure that this is one person over some time span, rather than just a single frame where I say, this frame, is this a walking person? That can be quite ambiguous, right? If I have one frame like this, am I standing or am I walking? But if I see 12 frames of somebody moving, I would classify that way. Are they generalizable with? Yeah, this is a hard thing. So often occlusion can be difficult to handle, especially as longer times. So people will link two different tubelets in time. So if there's an occluder in between, you'd like to classify this as walking, classify this as walking. But these are actually hard problems, right? So I think we don't have a good algorithm and kind of methodology for dealing with this, right? People who are occluded, people who change actions over long time spans, and that's why recognizing complex actions and localizing them is very difficult because people become occluded, they change what they're doing, they change appearance over time. And so that's why I do feel like open research problems are on, these types of architectures have a lot of limitations, right? You need to be able to track people well over short amounts of time. You need to be able to link them. Building similar types of things or something different that could actually handle multiple moving people who are occluded is interesting research. Okay, so the next level of detail of problem I want to talk about is what's called group activity recognition. So this again is about analyzing scenes. So again, either in the surveillance context, sports analytics context, or robotics types context. And again, if you're interested in these areas, these are examples of data sets that people use to validate their methods in this. So this is also very important for Canada. I think this is sponsored by CIFAR, and CIFAR is a Canadian research organization, so I have to make sure that our work is important for Canada. It solves a very important Canadian problem, which is who has the puck. By the way, do you know who it is? Who has the puck in this scene? I guarantee you that there are 0 puck pixels, right? There are no pixels in here that are actually from the puck. But if you look at the body pose and body shape of all these people here, it's the guy at the front right, okay? And so the reason I think we can do this is we can kind of analyze the whole scene and look at what every individual is doing, and based upon their body pose and their relations, we can figure this out. We actually built algorithms that do very similar things. This is the output of one of our algorithms. The pink colored box is supposed to be around the person who controls the ball in this field hockey match. And it's sort of flickering back and forth. When it has an X on it, it's incorrect, but we actually built algorithms that kind of analyze the body pose and spatial relations and temporal relations between people to try to figure out who is likely to be the one controlling the ball, who are the people who are attackers, who are defenders, what different roles are they playing in the scene. And again, we did this without being able to actually track the ball. We can do that just based on the body pose. The way in which these algorithms tend to work, there's a whole set of them. They generally use what are called person-centric representations. So what we do is we start off by detecting and then tracking people, maybe forward and backward in time if we're allowed to batch process a video. And we get a sort of a zoomed in then person-centric representation that characterizes what is this one person up to. And then what we'll do is we'll build architectures that kind of aggregate that information over the entire scene. So here's an example of what one of those looks like. It uses kind of hierarchical LSTM models, where what you could do is take each of the N people in the scene. For each of them, you have a track of what that person's doing over time, feed that into a recurrent neural network structure to get some representation for what that individual is doing, and then have various types of aggregation operators that could aggregate those over the entire scene, and again, have a recurrent neural network structure that can analyze that as it varies over time. And the output of this higher level LSTM would be in the whole scene, what's happening right now, what's going on in terms of the group activity that's present. And people have done variants of these. There's a few years ago work on kind of adding in attention-based models on top of these as well, where you can say, I have this particular person in the scene, that's a person that's very important, let's have attention weights that vary over the different people in the scene and use those to help characterize what's going on as a whole. In subsequent work, people have worked on kind of doing what's called social pooling, where rather than just doing kind of an entire attention map over all the people in the scene, you can have individual people in the scene that will get kind of attention different from each other. So one person's representation will be affected by a certain group of neighbors or people who are important to what this individual is doing. So the so-called social pooling algorithm helps to get representations of people based on the context of what's around them. We've also built methods that can be used in kind of encoder-decoder architectures of that type. So we built ones that kind of look at hierarchical relationships where we can take in, again, individual people in the scene and then build sort of small graphs that relate different people in that scene to each other and build up hierarchically from there representations about a person. And we've done that both in kind of a supervised setting, which is what's visualized here, as well as in this kind of encoder-decoder architecture that can be used in an unsupervised way to build representations for people based on what's happening around the scene. So similar types of things are used for just analyzing actions, not even from video input, but also from just trajectories. So we could just have positions of people over time. So this sort of shows an example of kind of trajectories of people in a basketball game. You could ask various questions like, which team is this? Who was player X? Will this shot be successful? So the types of architectures we use for doing this, again, share a lot in common. We've built what we call sort of share-compare trajectory networks, which analyze the motion of each individual person via a convnet that takes in one of those, and then stacks those together and combines them to analyze pairs of people and what types of interactions are between them. So these things are actually remarkably powerful. So we did experiments with these sort of analyses of spatiotemporal relations over just trajectories on NBA data sets. So there are these great data sets that are out there that are about basically have the trajectories of every single player in every single NBA game. So those are extracted from a multi-camera tracking system. They're quite accurate these days. 137,000 possessions, so like one end-to-end possession in a basketball game. So we built these networks, and basically, as an example of a task, we trained them to say, how well can we classify one of these possessions in a game just from the trajectories according to which team this is? So if you just saw the motions of the players that are back here, so if all you saw was this, would you be able to tell which team is the red team or which team is the blue team of each of the NBA games? It turns out that you can do that quite well. So from just a single possession, we can get 25% accuracy on which team this was. For people who aren't familiar, this is sort of like a 1 in 30 type guessing if you went just random chance. And if we aggregate that over all the possessions in a game, so again, just from the trajectories, we can be kind of 95% accurate on which team was this in the game, just based on how the players move. We've done similar things for kind of predicting shot location. So we can take in the trajectories of the players, and then, as you're saying, like predicting in advance what's going to happen, can I predict where the next shot will take place in a basketball game just based on the trajectories? So first, is this a hard problem? Do you know what's the most common location for a shot to take place in a basketball game? You discretize it into these 14 different zones. Any guess? Wouldn't
it depend on the era that the game is occurring in?
It does. So if you just had to guess, like blindly, prior, what would you say? Yeah, it's 0, it's right under the basket. That's the most common thing. So some large fraction of shots take place under the basket. Okay, so that's kind of one very, very simple naive baseline. The other naive baseline was, if I have trajectories of all of the players, and I know who has the ball, and you ask, where is the next shot going to take place? What's another good thing to guess? Whoever has the ball right now is probably going to take the shot. Okay, these are kind of two very simple baselines. So we built methods that are trying to predict where the next shot is going to take place. And this graph is visualizing time to when the shot is going to take place. On the right-hand axis, this is at the moment the shot is going to take place. The blue line is this just always guess the most frequent location for a shot to take place, which is under the basket. So if you always guess that, this is kind of your baseline performance. The other baseline that we use, we have variant here in yellow, which basically says we should just guess where the ball, that's the red line, you guess where is the ball right now, right? So you can guess one of those, where is the ball right now? And if you're far away from the time when the shot is going to take place, guessing where the ball is right now may be inaccurate, but as you get very close to when the shot's going to take place, it becomes more accurate. And so we were able to build methods that are sort of visualized in this yellow curve that can kind of analyze the trajectories of all of the players and predict in advance of when it's going to take place more accurately than just guessing the random shot location or guessing where the ball is right now. We've built similar types of methods that can analyze kind of sequences of actions and predict when and where is going to happen next. So we've got methods that can kind of take in sequences like, this is a hockey game, there's a pass, this pass has been received, the puck has been carried over the blue line, what's likely to happen next with some probability distribution on what and as well as when that's likely to take place. Okay, so this section is about kind of understanding like big pictures of scenes, people interacting with each other. It's more of a holistic view of activity understanding, not just the actions of an individual. And again, I feel like there's interesting work that's still open in this area around how do you learn from limited data, how do you generalize to unseen compositions, so things that are rare or haven't occurred much before. I might not have enough training data for that, zero-shot, few-shot learning scenarios. It's also interesting to think about how do you represent these sort of complex scenes. It's not clear right now what are the right representations. People have tried lots of different things, but you have variable duration actions, multiple activities happening at the same time. How would I represent that? There's also a lot of effort in kind of adaptive pooling operators. So if I have representations of what individual people in a scene are doing or where are they, how do I aggregate that to get some composite representation over the entire scene? Finally, like grounding, so how do I know who or what in the scene is evidence, as well as predictive models. So let me pause here again before I move on to the last section on generative models, if people have any questions about this kind of group activity and predictive stuff. Right? So there are methods that use what we would call kind of interaction graphs. I'll give one example, this one. We build these sort of graphs just spatially. So what we do is we say that these people are interacting with each other because they are spatially proximal to each other. Other work in this vein, I'd say like the social pooling or the attention-based pooling do kind of interaction graphs or kind of relations between people based upon attention models or features that are derived from individuals. And that does seem very important.
Are they scalable? Like, these are like 20 objects?
Well, that's a good question, yeah. So I mean, in this setting, you're unlikely to have more like 10 people in a basketball game, or your viewport is not that large in a video scene typically. So the largest people have sometimes, Alex Alehi actually, who's done much of this work, did things on analyzing train station videos. So you have large crowds of people ordered in the hundreds and trying to build things over there. I feel that the interactions there are not very large scale. So it's not that a person at one time interacts with somebody far, far, far in the future. So the interactions are limited. Right, so in terms of like agent in a box, like in a very closed environment where I play, so there's a lot of work that's has been done at CMU on this for many years on kind of multi-camera dome systems where you can get to a point where you get very few occlusions. So much of that work was more about 3D reconstruction rather than just activity recognition, but when you have multiple people in the scene, it becomes harder. So you have a single agent in an environment like that, you just plaster it with cameras and you can basically have very few occlusions. It's this sort of thing. If you have 5 people in the scene though, it can become much more challenging. But yeah, Hyun-Soo Park and some others from CMU have done great work in that direction. Yeah?
You mentioned that occlusion is very hard, but how was this occlusion? Like the object was occluded at the first frame, but then later, like the green one is in front of the other one, and then it's got disoccluded. How do you solve that? And the other question I have, do you use object tracking for this kind of stuff?
Yeah, so this question about occlusion, like how do you solve occlusions? I think that, and then like do you use object tracking? So yes, we use object tracking in these techniques typically. How do you solve occlusion? As you were saying, at some point things are visible, at some point things are not visible. You generally have algorithms that link over those time spans. Right? So usually what you do is you build an architecture like those microtubes where I track when I can track. When I can't see things, I don't know what happened. I track over here where I can track, and I have a mechanism to say those were the same person. That's usually what the architectures look like. Yeah.
Related to the previous question, so I'm wondering, like I'm was thinking in scenarios like NBA, where there are a lot of similarities in terms of players' appearances, because like they have similar codes. What are the like? I was thinking that that's probably like one of the challenges, like you need to somehow do identification as well.
Yeah. So.
Track
Yeah.
people's motions in the videos. How is that addressed in the current?
Yeah, so it's actually pretty amazing these days. The state of the art in that is very, very good. Hockey is even harder. Hockey, you know, they have like two colors, basically, who's who. And, you know, there are commercial systems that do that from broadcast video in real time incredibly accurately. Basically, if you can see the player's number at one point in time, you maintain that identity while you can't see it. Like if I'm like this and you read the number and then the person turns and goes, you just remember that that's that person. And you know, in soccer as well, everybody enters the penalty area. It's a big mess for a while, and then when they spread out again, you can get their identities back. So yeah.
Are the videos recorded from different angles?
Yeah. Often you want multiple views to do this well. Yeah. So single view can be challenging, but again, it can be possible to do this. The accuracies aren't as good, but for multi-camera systems, it's quite accurate. Any other questions? Okay, cool. Okay, so the last segment of things I wanted to speak a bit about was generative models. So, you know, people are probably excited these days. It's pretty amazing what we can do with GANs, VAEs, et cetera, on generating really cool videos. So I have a little video about kind of like generative models. And the story here is that I do like sports, so I actually like soccer a lot. But I'm not that good at soccer, okay? But I thought, well, hey, you know, I'd really like to be in the World Cup. So wouldn't it be fun if I could take a video of me running around and then, you know, kind of, you know, jog back and forth a little bit and then put me in the World Cup? That would be kind of fun. So take a video of the World Cup, detect and track a person, take that person, generate frames of me that would be really nice for that, and then rub that person out and put me down there in the bottom, and there I am going to chase after a ball. And you know, if one Greg isn't enough, why not have two? And if two Gregs isn't enough, then three. And why don't we just go replace the whole, in this case, American national team with a Canadian? And if you follow the Canadian men's team, this is the only way we're getting back into the World Cup. The women are awesome. They're so much better and more fun to watch. But this, we also just kind of switch teams ad hoc and so forth. Okay, so generative models are super cool. Does anybody know like when that was done? Any guess? It's 2003. Okay, so we were doing kind of things like this in the past. If you had to say what the model was, it was what you call non-parametric density estimation, or like nearest neighbor matching, and basically putting in a person based on what happens. So a lot of great things have happened since then, and we've worked on this problem as well. You know, back in 2003, we were doing methods like this and very, very naively to just kind of copy pixels. Right? If you wanted to do this kind of generative model, you just sort of wipe somebody out, find a match of kind of a scene that looks like that, and just put that in there. This was okay, but it didn't work very well. It definitely didn't generalize to things you've never seen before. I'm not going to go score a diving header, right? There's no way, I can't do that. There's no way there's going to be kind of a video of me doing that. That's not possible. So it really had very poor generalization abilities, very inefficient with the data. If I had to kind of characterize things, it's a very clunky old automobile type of thing. It's like, yeah, we got pixels, we'll just replace it. It's a very inefficient type of thing. So fast forward like 15 years, and there's been tons of amazing advances in what's happening here. I'll show you some of our recent results on kind of generating things. The things that I think are really cool about them is that they are data efficient, and they let you compose and generate novel things that you've never seen before. And I'll show you some examples of what I mean by that, but it's still pretty hard. Like, we want to be able to generate things that are difficult. So we have kind of ability to be compositional about our generation, to be modular about it. I think of it as kind of like this super efficient vehicle. The other thing that's different about our field in 2003 versus 2018, the types of companies that come and recruit at summer schools and so forth look much more like this type of car company and not like that type of thing over there. It's like super exciting, lots of people in demand and so forth. So I'll give you just a brief highlight of some work that we did in this area recently. This collaboration with Eric Jawe, one of my students, and a bunch of other people at Disney and Caltech and UBC. So when it comes to generating videos, what we like is a few different things. So first of all, it's very important that the things that we generate actually look like a real video. So what we like to do is generate novel frames, and each of those frames actually has something that we care about. But beyond that, it kind of should be realistic in the sense that it's a reasonable interpretation of what might happen in the future. So for example, if I have the frame down here on the bottom left as my first frame, I'd like to generate a following sequence that's kind of reasonable. Like that's a thing that could possibly happen based on that first frame. For example, the person's appearance won't just change dramatically. It should still be the same person in frame 10 versus frame 1. There should be some temporal smoothness to this, that what the person was doing at the beginning continues on in the time. And this is very difficult, like making visually realistic videos, again, rapid progress in the past few years, but this is a challenge, trying to make things that actually are plausible. And then also being able to handle kind of the non-deterministic future. So if I actually want to be able to generate what happens next, we need to be able to capture this kind of multimodal distribution of what's likely to be out there. So this particular work that we did was focused on using variational autoencoders. You know, GANs and they're both great at doing this. VAEs have potentially an ability to capture distributions over future frames in a way that uses a latent space of variables. So I don't know that people have heard of VAEs here, so I don't want to dive into them too much in this thing, but basically we have a particular type of VAE that's able to handle temporal data, which is done by throwing a recurrent neural network over top of the latent space that you have in a variational autoencoder. For those who aren't familiar with them, a very, very quick intro to them is that what we do is we kind of train these models by having an encoder that can take a video frame, xt, that's a frame at time t, pass it through this encoder and basically match it to a distribution over a latent variable z, which can also be used to now generate novel video frames. And at training time, what we try to do is make sure that this mapping of the video frame via the encoder through to a distribution over latent spaces, mapped through a decoder, matches what was happening in the original input, so that this sort of x tilde at the top matches what was thrown in at the bottom. So to generalize these to temporal models, what we do is we have kind of a recurrent structure that's built over top of the latent space. And what's kind of the current challenge and what people are working on right now is about making this structure able to be controllable. So generating videos where you're able to actually control what the person does or what the person looks like or fits into some environment. So like that soccer video I was showing you at the beginning, actually being able to generate a video like that that puts someone into a real environment, you can control what they do, is still quite challenging. So our work was toward that. In particular, we worked on two aspects to this. One is maintaining temporal consistency, so the identities don't change, the smoothness of the videos is sort of visually realistic, as well as having some high-level control over those videos. So the couple of sort of modifications we made to these architectures to do this are first to kind of have a way of using the latent spaces that we generate, the Zs that we sample from there, in our recurrent structure, as well as adding structure to this latent space that's in this variational autoencoder. And just to zoom in a little bit on what this latent space looks like, it actually allows you to have kind of control variables that would say, I want the person at frame t to be walking, or I want the person at frame t to be running. I can have these control variables that are in here, these attribute controls, and they can be things that are either multi-class or single class that basically say, what is it? There's some property of this frame at this time that I want to control. And we built up a recurrent structure on top of that, as well as a variational autoencoder that can kind of maintain temporal consistency as well as allow you to have control over the sequences. So what this looks like, here's some sort of captures of these frames that are generated over time, what we were able to do is sort of say, I want the person to do certain actions at certain times. So each of these stripes is one of the sequences that we generated. The blue color here is used to denote we want the person to be walking at this time. This orange color is I want the person to be running at this time. And this blue color is I want the person to be walking at this time. So each of these sequences is kind of composed of these controllable actions. And what's interesting to me and what I was excited about is that we were actually able to generate these transitions between actions that don't exist in the actual training data. So in the training data, what you have is you have sequences of just somebody walking, or just somebody running, or just somebody skipping, or doing jumping jacks. The training data are all kind of a single action. And what our method was able to do is to learn how to generate smooth-looking videos that have these transition points. For example, between walking and running, which is visualized in these two top rows, or between doing jumping jacks and then doing these sort of sidestep motions. So how do you smoothly transition between those actions is something that, back in 2003, we had no way of doing that. It was not something that was possible. If we've never seen you do that before, there's no way that we can generate that type of motion. So these methods actually seem able to generate those in-betweens, and I think that's again, what's exciting. Being controllable and generalizing to unseen compositions like jumping jack to sidestep that don't exist in the training data. Okay, so maybe I'll just do the concluding remarks first, and then I'll take more questions, about 15 minutes or so at this point. So I've shown you kind of a quick sort of hour of what's going on in activity recognition these days. There's a huge variety in sort of where this applies, and it's everything from kind of sports type videos to YouTube videos to Vine or other types short social media clips. Really a lot of challenges in temporal labeling. I feel like the goal, like what are we trying to achieve with this field, is the following. We really want to be able to label every single voxel of a video at multiple levels of detail. So at this one highest level, we'd like to do tagging, where we take in a video like this and we throw tags on it, like this volleyball game, this is the first set, it's an indoor scene, etc. I'd like to go down to the level of details of what all the people are doing in every single frame. I'd like to know semantic segmentations, or where are they, and I'd like to be able to predict what's going to happen next. Right? So I think that probably the ball is going to end up in one of those areas. I think that the next activity is likely to be the left team winning a point, but there's some probability that the right team is going to make a pass. That's what's likely to happen. So this is kind of the ideal vision that we have. We'd like to build systems that can do all of these things together, and we're quite far from that today. So I have a slide of kind of like common threads about this understanding of every voxel, and to me what I think are interesting open directions for future research that I've highlighted along the way. So last thing, I'd just like to highlight, we have this awesome community crawl that's organized for tomorrow. I'll be at Borealis AI. You have a stop on at our office in Edmonton along the way. Please feel free to come through and chat with me if you're interested about Borealis. We're hiring full-time and intern positions. We also have a fellowship program for graduate students. If you're a current grad and you're looking for funding for something, the application's open next month. Please see that website for information on that. Finally, I'd like to conclude with thanking, I get to stand up and talk about the work that my students and postdocs did, and so a big thank you to them, because they're the ones who did all of this work. So thanks very much for your attention. I'm happy to take more questions.
So in generative models,
Yeah.
either you're generating images or videos.
Yeah.
And you often see, especially when you're generating high resolution
Yeah.
versions of images or videos, that the generated images, videos somehow don't follow the physical world. For
Yes.
example, faces are not
Yes.
symmetric,
Yes.
or the hair
Yeah.
disappears when you're flipping.
Yeah.
And this kind of thing. Have you, what are your thoughts about this, and have you thought about incorporating some physical knowledge from, I don't know.
Yeah. It was a really good question. I think it's a question about physically impossible or violating constraints when you're generating videos or images, and how do we address that? So we had a NeurIPS paper last year on image generation of compositional scenes. And they'd be objects from what's called the clever data set, where there'll be a shiny sphere next to a matte cylinder. And there'll be some interreflection artifacts that should exist there. How do we make sure that things like that are actually present in the generated images? And my feeling is that likely we'll start to see people generating either in 3D or in BRDF space. Like Angel actually has done a lot of cool work on 3D vision, and I think, thinking about like how do you model shapes, how do you do that generation, and maintaining those 3D relationships, probably you should be generating them in 3D. Then you can likely generalize better and maintain those things. So objects cannot penetrate each other, for example. If they're rigid objects, that should be something that's modeled by 3D relationships likely.
Do you have a solution of how to combine these kind of journey models that only learn from data and connect it to a physical simulator that is differentiable?
Right. Yeah, so I mean, again, I pointed, we had this NeurIPS paper where our goal was to learn sort of compositional priors in a VAE, where you could kind of have language type relations and then say that, like if I learn about blue and I learn about spheres, how do I combine those two sources of knowledge to generate blue spheres? And again, I feel like that kind of like programmatic generation is likely to be a path forward toward that. Right, so there's a lot of work on kind of like probabilistic programming and how do you generate things via a language and a representation. I feel like that might be a direction to explore for that type of learning. It's like Frank Wood and Nando de Freitas have done lots of great work in those areas, and I feel like that might be a direction to explore for it. Yeah.
I asked a question about your attentive model.
Yeah. Yeah.
So, without reading up more, could I ask, like, how is your, like, what is the key assumption you put in the attentive model that you can infer the same everything? Is that because you let them to learn a factualized representation of the identity and action?
Right. So what's the? I didn't quite get the question. Sorry.
So the question is like, what like key features in your attentive model
Yeah.
allow you to infer the same or kind of the same thing?
Right. So the key features in this particular work. So yeah. So in this particular one, the couple of key features are the following. So one of them is that we have holistic attributes that these are sort of A1 through AN, which are going to be things that are in part of our latent space, basically, that are controllable things, that we have ways to learn them as well as ways to use them at test time that can specify this must be a person who's walking. So we have that part of the space. The other thing that we have is the way that we split up the various posteriors that we use in training this model, and the fact that we actually pass the sampled value of a latent variable through the recurrent neural network structure helps to maintain things. So one of the things that can happen in these models, especially in VAEs particularly, is that what you're doing is you're formulating a prior. So at test time, you're kind of sampling from a prior. And you draw samples from that prior. If those samples are not consistent over time, you can get sort of drift in some things that you care about maintaining. So what we were doing is we were seeding the prior at the next time step via the sample that we drew from the prior at the previous time step, which seems to help maintain coherence over time. Yeah.
Maybe this is similar to the idea of the prior, but do you find some of the issues with decoders that you see in typical images, like checkerboarding and those kind of things, are they compounded through the LSTM?
Yeah, I mean. Right, so again, like, I think that there's a wealth of work on kind of like this decoder block, like how would you actually build this well? I would say a big limitation of our current work, if people know this data set is really old, it's called the Weitzman Human Action Data Set, it's quite limited in its variety, right? The backgrounds are relatively simple, the people's appearance are relatively simple. We're not generating like really high resolution, complex facial expressions. So I feel like a lot of the improvements that have been made in just kind of how do you do either RNN, like spatial RNN-based decoders or better GANs for generating high-resolution images could likely be applied here. But again, I feel like what's really hard is just that variety of background. Like if you actually had a moving background, for example, trying to deal with that is quite challenging. Right, so many of these methods can kind of capture velocity via what they're doing. So let me just show you one example. So here's an example of a network structure we built for analyzing people's trajectories. So the input to this is XY locations of each person. It's XY in, for example, court or rink coordinates. But we have that over time. So like position, 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 position of the person. We put that through a convolutional network that's operating over XYT sort of thing. So it has only position as input, but you could have a filter in that convnet that looks at velocity, basically. It can measure speed by looking at, is this a person standing still? You could have a filter that's basically learning that, versus you could have a filter that's learning, is it a simple translation, a fixed speed, versus is it like a move to the right, then a move to the left? You could have filters that are basically firing on those types of things. The network can learn those. Yeah, so we did not explicitly encode that. And I think you find the same things with, like it's kind of a design choice. People, like back to the beginning, people look at neural network architectures for analyzing video and, do you really need the optical flow stream or not? It might not be necessary to do that because if you just use a C3D type network, maybe it can learn about optical flow implicitly. But it actually does seem useful still to have that kind of, well, I know about motion, I'll do that. You probably get better efficiency in parameters by doing that. So people do often still hard code the fact that there shall be optical flow in these networks. Though you'd think, can't we should be able to just learn that, you'd feel. Yeah. I mean, that's a good question. Like, how do you quantify smoothness? As you probably are aware, it's not trivial to measure the performance of a generative model. And so, we do have tables of numbers, and we use things like inception score, which will basically look at how well does a classifier that's trained to classify videos believe that the videos we've generated are people walking, for example. Does that require smoothness? Not exactly, but maybe that classifier is better based on that. I mean, you can do user studies and so forth, but those are challenging to run and expensive. Yeah.
I just wonder what kind of tracking method you use to achieve reliable tracking performance?
Right. So what type of tracker would you use for reliable tracking methods? I would say you should go talk to some companies that work in this space. At some point, these become like heavily engineered systems that are, it's not what's published in a paper. It's, you engineer a system that does this well. And often it's, I think someone asked about this as well, multi-camera systems are often really important, right? And you need a lot of dirty tricks to handle occlusions and how do you aggregate information and so forth. But you can learn to track. Like you do, at a high level, you would kind of learn how to track. Right? You have a learning mechanism that's learning how to do that, integrated with your detector, and generally that is what you do, but you usually do that from a multi-camera system and so forth. Yeah. Yeah.
Have you tried deploying any of these on those constrained platforms like Go, mobile?
Right. So personally, I have not tried deploying these, but there are many efforts in that direction. Again, I think it becomes a little bit more toward kind of the industrial applications where, for example, for sports analytics, you might be interested in, can someone just hold up a cell phone at his daughter's soccer game and get sports analytics data out of there? I think there are a lot of technical challenges toward that, but I think if you're doing that for a 2-hour-long video, there'll probably be battery considerations toward doing things like this. And there are just a lot of issues of this type. I feel algorithmically it's not impossible, right? But I think there are other challenges to that.
So going back to the previous slide, how do you structure your latent space? Are you doing sort of disentangled?
Right. So the latent space basically does not have a direct disentangled representation in this work, I would say. There's a Z vector, right? The prior that you get for that, so for example, like what should the prior distribution over that Z vector be? It takes into account these holistic attributes. So the values of these attributes, these will be things that will be set, not one hot, you can have multiple things, but let's say it's one hot, it shall be walking. That, as well as feeding in from the previous time step, the recurrent neural network output will be used to construct a prior over that Z vector. So it's not a disentangled representation in this case. Ziwei, one of my PhD students, has another piece of work that does kind of factorized latent spaces. That work was in CVPR 17. It was about analyzing audiences of people and their facial expressions. So you'd like to have temporal and spatial for the face, as well as a group of people. How can you build a VAE that can handle that? And they factorize over time, over identity, over facial landmarks. So we do have work like that as well. Okay.
Is the camera calibration for this kind of stuff also matters for training?
Yeah, exactly. The camera calibration, so you're talking about multi-target tracking systems, exactly. Like you're going to do camera calibration, you're going to know what views, like it's a lot of detailed stuff to make that work, exactly. All right, I think the time's at 0. Thanks very much.